Hiya. So in this video, we're going to be talking about inner products in Euclidean vector space. So much of the geometry we learned in school is centered around distances and angles, and like you can, I don't know 100% how it worked here in England, but at least in the US, like we were learning about triangles and how like one triangle is similar to another triangle, and like stuff like that, right? Like what's the angle between two things, sine, cosine, blah 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 blah. So we learned like and how far things are from one another. So we're gonna try to replicate that into an arbitrary vector space. And so for us, the key to this is going to be something called the inner product. Now, generally, there's something a more general definition of inner product for vector spaces over other fields. But because we're really going to be sticking over real vector spaces like R, remember how in the very first lecture or talk we kind of said you can have rational numbers, you can have finite fields, etc. Since we're going to stick with R, we're just going to talk about inner products. So it's not really something too big. And you'll kind of notice already in the definition, I'm already saying that an inner product or scalar product on a vector space. So in other words, there's going to be some kind of sense of scalarness to this. And we'll kind of see what I mean by that in a second. So an inner product, on a vector space over R is basically some function, and we'll always denote it with this little fun little bracket symbols, right? From V cross V to R. So what this is kind of saying, if you haven't seen notation like this before, is it's going to be maps like this, which gets sent to some number X, for example. So here X is in R, and then V and W are in V. This is kind of the way to think about this if you haven't seen notation like this before. So what this is saying is we're going to have some conditions. So for every single thing here, for every X, Y, and Z in V, and for every scalar lambda and mu, we're going to have three conditions. One is symmetry. And what's the symmetry condition saying is X product Y. Oh, these are vectors, yeah. So I should have lines under. X, Y should just be the opposite, right? So Y, X. These should not matter. I shouldn't care, right? Second, my scalars I should be able to pull out. Not only that, but I should be able to distribute. And this is called linearity. So linearity is basically saying if I have lambda X plus mu Y, and I cross product it with Z, I've inner product it with Z. So here I'm going to distribute, and I'm also going to be able to pull out a thing out. So here I have, a scalar out. So lambda X Z plus mu Y Z. So here a kind of thing to note, unlike what we did with vectors, here lambda of X Z does not equal, so we don't just multiply inside. We don't do that with every single term. What it does equal is we can either put it in front or we can put it in the second component. It doesn't really matter. Now, why can we put in the second component? This you actually have to kind of show, and this is coming from symmetry, right? So what you do is you take lambda of xz, you flip xz, you pull the lambda in, and you symmetrize again. But try it out. There's one other condition we need, and that's called positive definite. So for positive definite, what we have is the following. X inner product with X, well, positive definite makes it sound like it should be positive. It's positive. That's basically what we're saying. What's the word definite? Well, definite is basically saying it's only 0 when X is 0. So with equality, if and only if X is 0. So here, remember, the 0 with a bar under is telling us it's the 0 vector. Now, this is actually going to define us a particular vector space called the Euclidean vector space. So Euclidean vector space is a vector space where we add an inner product. So we're going to also add an inner product to it. And that's all. We'll talk about, we'll give some examples for Euclidean vector space in the following video. So I'll see you there. Peace.